Write operation in SRAM. How is data written? Writing data into an SRAM cell means changing the value already stored in the cell to a new logic value. Unlike a read operation which simply senses the stored data, a write operation must force the internal storage nodes to switch states. Before the write begins, the write driver places complementary data on the bit 2-bit lines BL and BLB. For example, to write a logic 1, BL is driven high and BLB is driven low. To write a logic 0, BL is driven low and BLB is driven high. Once the desired data is present on the bit lines, the odd line is activated. This turns on the two access transistors connecting the bit lines to the storage nodes inside the SRAM cell. The stronger write drivers on the bit lanes overpower the existing state of the cross-coupled inverters, forcing one stage node high and the other low. As soon as the internal nodes switch, the positive feedback of the cross-coupled inverters reinforces the new state. Finally, the word line is deactivated, isolating the cell from the bit lines while preserving the newly written value. Example, if BL is 1, BLB is 0, odd line is high. Access transistors turn on. Storage nodes switch to Q equal to 1 and QB equal to 0. Cross-coupled inverters latches the new value. Odd line returns low, completing the write operation. Why is writing harder than reading? Writing in generally more difficult than reading because SRAM cell is intentionally designed to resist the changes to its stored value. The cross-coupled inverters create a strong positive feedback loop that continuously reinforces the existing data. During a write operation, the write drivers must overcome this feedback and force the cell to switch from one stable state to other. If the pull-up and pull-down transistors inside SRAM cell are too strong, the write drivers may not be able to change the stored value, resulting in a write failure. On the other hand, if the access transistors are made too strong, is improve writability. They can reduce the stability of the cell during the read operation. Therefore, SRAM designers must carefully balance read stability and writability through proper transistor sizing. Another challenge is modern processors operate at very low supply voltages to reduce power consumption. At lower voltage, transistors produce less current, making it more difficult for the write drivers to flip the stored data. This is one of the major design challenges in advanced SRAM technologies. Reasons writing in header, the cell actively tries to retain the old data. Positive feedback opposes the incoming data. Write drivers must overpower the storage latch. Power supply voltage reduces the write strength. Designers must balance write ability and read stability. What determines write margin? Write margin is a measure of how easily new data can be written into an SRAM cell. It represents the amount of voltage or current required to successfully changes the stored value with causing errors. A larger write margin indicates that the SRAM cell can be written reliably under different operating conditions, while a smaller write margin increases the probability of write failures. Several factors determines the write margin of an SRAM cell. The relative strengths of the access transistors and the pull-up pull-down transistor are particularly important. Stronger access transistors allow the bit lines to more effectively influence the storage nodes, improving writability. The supply voltage VDD also plays a significant role. As VDD decreases, transistor drive current reduces, making it harder to override the stored value. In addition, manufacturing the processes variation, temperatures changes, and threshold voltage variation can all affect write margin. To improve write margin, modern SRAM designs often use rise assist techniques such as temporarily lowering the cell supply voltage, boosting the old line voltage, or strengthening the write drivers during the write operation. These methods helps the bit lines overcome the cell's positive feedback without permanently affecting read stability.